Hello, welcome to the Sunday Science Q&A. This is the 20th one since lockdown. We've also had of course, slightly every now and again. We did see Shambles, which is still up on our Cosmic Shambles website, which was about a 4.5-hour show of lots of different sea mayhem, including a very interesting reading of of Moby Dick and bits of Rime of Ancient Mariner, and we had bits of British Sea Power and Lem Cisse, and it was lots of stuff going on, and also our Cheltenham special as well from Cheltenham Science Festival, where we did a show to end Cheltenham Science Festival. A few things. So today's an astrophysics special. So we have two astrophysicists, and we also have our regular physicist, Helen Czerski, as well. And so if you have any questions you would like to ask, you can just go down to the kind of chat area, whatever area that is, and Trent will send me those questions, or I will also be checking on that. We have an enormous number of questions, so don't think in no way is this a plea for more questions, but if you have something in particular cosmological that you would like to ask, today is the day to do that. And also remind you of some of the other things, which is Patreon, which is very important to us. All these things going, as you probably, I think I've got one live date left in my diary now this year. The tour has been entirely wiped out, all of the other festivals, everything else. I have one date I think left in there. I think the 3rd of December tenuously remains within my 2020 diary, but that's why we need Patreon support as much as possible, because a lot of the things that we used before to kind of finance these we don't have anymore. So if you are able to support us of our Patreon, that makes things a lot easier for Book Shambles, for Cosmic Shambles, for the documentaries we make, the series that we make, all that kind of stuff. If you don't want to go to Patreon, then you can just support us by putting there's a kind of little tip jar at the bottom of this screen if you are able to. And of course, if you're not able to, we totally understand that. People are in precarious times, but if you are able to put something in the tip jar today as well, that helps a great deal. Some of the other things up to, as well as all the Science Shambles, which you don't have to watch, by the way. We also have audio versions of that as well. As I said, there's 20 Sundays worth and loads of other things that we've done around that. Well, but that's all still available, and also there's conversations about teenage mental health. There's a teenage mental health show, and there is the conversation that Brian Cox and I had with Andrian as well, which was for the Blue Dot Festival, and that was us talking about the Pale Blue Dot with Anne, and also about Voyager, because obviously she was actually the person who was in charge of the Golden Record and co-wrote Cosmos and Demon Haunted World and Comet and many other things as well. So that was a really lovely conversation to have. And our latest show and tell is with Jay Wilgoose of Public Service Broadcasting, and submit questions, by the way, is stayathome@cosmicshambles.com, or you can just tweet at Cosmic Shambles, or you can just go to the live chat. I'm going to start with my show and tell before I introduce everyone. This is it's such a beautiful cover. I don't know how well you can see this cover. This is the song Eugene Murray, who was a very interesting South African kind of lawyer and poet and activist who he wrote a very interesting book called The Soul of the White Ant, which was about his period of time of observing termites. This is a little trick he did, by the way. The Soul of the White Ant is actually about termites. The Soul of the Ape is actually about baboons, which are, of course, a very clever monkey. But this book was, as far as we know, the first time someone basically lived in the wild with a species to observe them properly. And the book itself didn't come out till 9 years after Jane Goodall started her incredible work in Gombe. But he actually did this in, I think it would be the 1920s, and the book, though, was released 34 years after his death. So this is a fascinating book. But the thing that I love about it, which will mean nothing to most of you, is I bought this the other day with no knowledge that this used to be the property of John Justin. Now, some of you, very few of you, maybe 3 of you will go, oh, John Justin. Yes, John Justin, the actor star of the 1940 version Thief of Baghdad, appeared in quite a few Ken Russell movies, and is in the tremendously unsettling ghost story Shalcon the Painter. So this used to belong to the actor John Justin. I didn't know that, and now I do, and it's mine, and leave it well alone. Welcome to our astrophysicist, who today, we'll start off with, because I don't think you've not been on in this season, Dr. Jen Gupta. How are you?
Hey, yeah, I'm okay. I'm set up in my daughter's, and so for show and tell, I was looking around. I was like, I hadn't really realised how nerdy I'd made my daughter's bedroom until I was sitting here gazing out at it. But instead of showing you all of that stuff, I thought I'd show something that if anyone's watched the Family Science Club that I was on a few months ago, you might have seen this. But this is a tactile galaxy. So I work on a project called Tactile Universe at the University of Portsmouth, and this is all about getting visually impaired people, finding ways for them to engage with astrophysics. And so this is a keyring version of what we've done. This is the Whirlpool Galaxy. And so what we've done is we've taken the black and white image of that galaxy, and we've looked where it's brightest, and we've just like raised that above the base. So it's hard to see on this keyring version. The ones we use in schools are bigger than this, but I didn't bring any of them home with me during lockdown. So yeah, that's my little show and tell. So instead of looking at the galaxy and looking at the shape and all of that kind of stuff, you can just like run your finger over it, and you can feel the shape. You can start to understand what structure that galaxy would have. We do them for the different colors as well. So if you look at the red light compared to the blue light coming from a spiral galaxy like this, they'll look different. And then we can start talking about why that is, the different populations of stars, all that kind of stuff, just from that little 3D printed galaxy that I've got there. So yeah, that's what I wanted to show.
I was on a project. I gave a judging panel for an Institute of Physics prize a couple of years ago, and the prize was given to someone who was working on astronomy for blind people using similar things. And it was brilliant, because you would think that that's a really hard transition to make, but actually she had this whole thing, and she had blind people who could feel the structure of galaxies, and it was such a cool thing, and we were all really impressed with her. Is that becoming more common now, or is that still a bit more unusual?
I think there is a bit more of a move towards this. There's several different projects in the UK certainly that are doing this. So we're Tactile Universe. There's Tactile Collider, which is doing very similar things but based on particle physics, so stuff going on at CERN. There's a lot of different projects, but I think what sets us apart is we really wanted to get the research out there. So this is really based on the research of my colleague Dr. Nick Bond, who leads the project, and he is a blind astronomer. So he is a rarity. Because a lot of people, as they're growing up, if you're visually impaired or you're blind, you just kind of naturally feel excluded from this subject. We've been told stories of like a young girl who was just taken out of her classroom when they taught space because they thought she couldn't understand it. So why would they try in the first place? So we're really trying to like combat that and get into schools quite early on, so that we want to do things that everyone can access. So, we don't take the visually impaired child to one side. We do this with the whole class so that everyone can experience the exact same thing.
Where can people get hold of these? Are they? Is it possible for people to purchase them?
We aren't selling them at the moment. If anyone has a 3D printer at home, I think that's probably becoming you can download the files. So all the files to print these are available on our website, which is tactileuniverse.org. But yeah, at the moment we haven't figured out how to commercialize it. I think we want to, because who wouldn't want a tactile little keyring of a galaxy? But yeah, if you go to tactileuniverse.org, you can find all the files to download it, plug it into your 3D printer, and away you go.
Right, yeah. I've got a question. I'm going to be asking both you and Katie very specific questions, because I'm currently on the chapter of my book. I'm writing about the size of the universe, and so in fact, anyone who sent questions in, bad luck. I got loads of them myself. But I'm trying to imagine what, because I think one of the reasons that people get a kind of level of anxiety when they first get some sense of how big even, the observable universe is because you can't manage to crush that down and place and make a visual image in your head. So when you are imagining the size of the universe, or the observable universe, what kind of goes through your mind? Do you have a kind of picture theory in your head as you're trying to gather it together?
I feel like we'll probably go to Katie, because I've got a very very simple answer, which is it hurts my head. So I don't think I've really cracked that one yet.
So how far, if you're pulling out, because I watched that wonderful thing again, Power of 10, which there've been lots of other versions of that since, but it still works very well. I think I first saw that when I was 8 years old. And so do you have a moment of you kind of pan out, and then you go, oh, I need to reboot myself, I've crashed?
I think get to go and fly the planetarium at Winchester Science Centre, and so I did a lot of that, like zooming around space. And I think for me, I can get my head around the solar system. I think probably because we've sent spacecraft out to all those planets. You know, we had the Rosetta mission going to a comet. We've got New Horizons, which flew past Pluto. So I can kind of imagine that in my head when you're in the planetarium and you do this and you fly out from the solar system, and then it's just so long before you get to anything else. And I think that's where my brain goes, nope, that's it.
So and also when because I was just reading about that time between galaxies. So that is that's not empty. That is it predominantly hydrogen ions? Would that be right? Or maybe I should throw to Katie now, because you've already kind of said, leave me out of this. I'm solar system based. I'm prepared to stretch to a galaxy, but I'm not going any further than that. So Katie, we're joined by Katie Mack, who has been with us a couple of times before, and some of you may well have seen on Sunday Brunch this morning, and whose book, The End of Everything, is one of my favourite, I could say one of my favourite science books of the year. It is one of my favourite books of the year. Really enjoyed reading it, and I would love to hold it up now and say my copy is actually used to belong to Oliver Tobias, who was in the 1979 version of Thief of Baghdad, but it's just my copy, and it was mine right from the start. Now, it's a fantastic. We'll talk about this later on, because I think we've got questions that reflect on this. But what do you, when you are, because of course your book is imagining the end, literally, of everything, the whole universe. So as you start to think about that, as you start to think of the big crunch or the big rip or whatever it might be, I suppose the big crunch, eventually that you can put that in the waste paper basket of your mind, but the big rip, etc. What are you seeing? Have an understanding of the fact that basically there is, when I say repetition, I don't mean like that kind of Max Tegmark, then there's us all over again, but actually that one area, large area of space is likely, is this fair to say, to be quite similar to it? So once you've got a square with galaxies in it, etc., that's basically, the laws of physics aren't changing. The laws of physics, as far as I know, are staying the same. So you don't have to keep making it bigger, because you go, well, it's kind of
hard not to have to deal with it, right? We just make everything look the same. Because I remember the biggest thing I've ever seen, and it wasn't the biggest thing I've ever seen, but my brain thought it was, and it was a tornado. And the thing about tornado is that, you know, clouds are normally there, but you don't really see them connected to the ground. Cloud base was probably 3 kilometers. So I was looking at something 3 kilometers big, but because I could see the connection, right? It was like seeing a line that connected the Earth to the moon. And then you saw it, and that hurt, and that was only 3 kilometers. You know, the brain, that was the shock that I can't cope with how big that is, because it's connected. Like, you need it to connect two things. No, and then you can put a scale on it. And the problem with like galaxies and space and all of that stuff is we don't have a thread that crosses the galaxy, and you go, oh, that thread. Now I understand. You know, there's no relative anything, and our brains really struggle.
Yeah, I've often wondered how much it would break one's brain to see a space elevator. You know, so that would be a thread connecting something in orbit, and I just don't know how that would feel. I've seen descriptions of it in science fiction, and I've always wondered, like, but what would it feel like to actually look at that? Like, would that just? I mean, I remember I saw a total solar eclipse, and that broke my brain because it was just so bizarre. It's just such a weird thing to see. Like, there's something, it goes into something primal in you that, like, the sky should not look that way. And I've often wondered if something like a space elevator would do the same thing. It would just kind of break all your sense of scale and how the sky ought to look.
So I think that might be it, that a lot of things which people can, if they want, or not even if they want, you know, attach an anxiety to and then not shift it, is something that actually you are meant to. Your brain is meant to go, and then you move on. It's meant to short circuit at that moment. Leave the short circuit. Once everything is cooled, you can then move on, and it will come back every now and again as a kind of memory. I presume your show and tell has been in front of our eyes all along.
Yes. So I figured it's here already. I might as well talk about it. So this chalkboard was a gift to me from the Perimeter Institute for Theoretical Physics, where I was doing a visiting fellowship. And the reason they gave me a chalkboard is because I was going to be doing a public lecture, and the public lecture became a virtual public lecture, and then we needed something to do visuals, and we decided, like, Perimeter Institute is really into chalkboards and equations, so, like, okay, well, I'll draw some pictures on the chalkboard as part of the public lecture, and then that'll be like the visual, right? And it worked really well. It was like a sort of Q&A thing. But then it turned out that when I was working with my summer research student, also remotely, it was really handy to be able to actually, you know, draw out equations and diagrams for her so that we could discuss the science. And so I asked them if I could keep it. And they said yes. So it is actually genuine cosmology on the chalkboard. And I realized this morning, because this was also in the background when I was on the Sunday brunch show this morning, and somebody was asking about, like, what are those equations in the background? I realized that they're actually somewhat relevant to the subject matter of the book that I was talking about on the show. So this bit here is the critical density of the universe. So this is the number that determines whether the universe will continue expanding forever or contract, and collapse on itself. So the idea is that the universe is currently expanding, and the idea is that all the gravity of the stuff in the universe should slow that expansion down, right? The expansion started with the Big Bang, and then all the gravity of everything should be slowing it down, and it was for a long time. It's not anymore. It's a complicated story. We can get to it later. But this critical density is the density of where that would exactly balance, where the gravity of everything would have exactly balanced the expansion. So that's the border between a universe that continues expanding forever or stops expanding and collapses down. So I was talking about this with my research student, and she was coding something up. So I was explaining that, and that's why that's up there. And then this line here is the Hubble parameter, which is the sort of current rate of expansion, or in this case, the rate of expansion of the universe at different eras in the universe. And so it's all about how to calculate how quickly the universe was expanding at different times. And then the other lines are about calculating how much matter there is in the universe at different times. And so it's all connected to this idea that how the universe is expanding in the past, how it'll expand in the future, sort of determines the fate of the cosmos.
What's great is, and this might only mean anything to Helen, because you might just be old enough, is you are one soft toy away from being the BBC test card symbol of the 1970s and 1980s. Mean nothing to you, Katie and Jen. You're probably too young to know that reference point as well.
Thank you for making me feel good this morning.
Well, I'm the oldest one. Don't worry. I'm just, if science is about honesty, I know it says your lecturing age, your agent says lecturing age 21 to 34, but there we are. Now, what have you got for show?
I have something which actually speaks to two of these things, because it's an event. It's an event that happened the year before I was born, since you've just pointed out how old I am. Thank you. But it actually speaks to, you know, when people look out into the universe, one of the things they get excited about is life on other planets. Now, I am a much more Earth-based person, but I remember I did geology my first year at university, and there are two lectures that really stand out to me from first year geology. One of them was Simon Conway Morris getting very excited about copulating cephalopods in the fossil record. And the other one was this guy, Professor Van Andel. So this is his book, and he gave a lecture called Serendipity. And the book, the reason I've got the book is I bought it because I asked him to sign it. It's one of the first time I ever asked someone to sign a book, this was. But the thing that was serendipitous, the thing that he talked about in that lecture, was the discovery of deep sea vents, because he was on the first expedition that actually saw life on the vents. So not just that there were, you know, black smokers and things coming up from the deep sea, but they went down in a bathysphere, in a submarine, and they saw things crawling around, so many things crawling around. And his lecture was this story of how they went and they dropped these things down and they were like, oh well, we're just going to see some rocks, that's quite interesting, and then it's just full of life. And it was such a gripping story. And even though I went on to do physics, it was one of the things that hooked me into the physics of Earth that I've sort of come back to now. And so I have this book still because because he signed it, but because the memory of that serendipity. And it's interesting, I think, because in a way, I feel that is us discovering alien life. Like the moment he describes is quite possibly the closest humanity will come to genuinely being sure that alien life exists, because, you know, life in the ocean is pretty alien. It's pretty weird. The different rules apply. It does have a common evolutionary ancestor if you go far enough back. But that shock of them actually finding it is what we've been waiting to replicate with exoplanets and the search for life, and maybe that was it. Maybe that's as close as we ever get. So anyway, so Serendipity, that was his lecture. It's always stuck with me.
That's brilliant. That's what year was the book out?
So the book was first published in 1985, but the cruise, the expedition where they saw life on the Black Smokers, was in 1977 on the Galapagos Ridge.
Brilliant. That's it's nice to ask for it. Once you ask people to sign books, there's no Patrick Moore got everyone, and whenever he did any show with anyone who he had the book of, he would always get them to sign it, because he had it's a nice thing when you've met someone or worked when the work means something, I think. Right, Jen, we're going to start with you on the questions today. I'm sorry for insulting you, Helen. It wasn't meant as an insult. It was just meant for accuracy. Well, it wasn't even meant for accuracy. Oh man.
Well, we should all be less embarrassed about these things, right? You know, we have interesting lives. We've been around the sun. I shouldn't react to it in the way that I did, really. So it was just you have to mention it. I'm the youngest of three, and everyone thinks I'm the older brother. So not only am I the oldest here, I'm also the worst at aging as well. Yeah, but we know you spent a long time in the attic when you were working with Brian. We know.
Yeah, I know. It's been the agony. Why I'm aging now when I'm at a reasonable distance from Brian, and have been for the last few months. It's normally only proximity where the age
it's like? Happens. It's like time for you passes at different rates depending on how
the
him.
Proximity term.
Like the relativity of the cocks.
Yes. For anyone who's seen the Tony Scott film The Hunger. Yeah, it's so the first question, this is from Lily, who is 6 years old, and feel free to pass the questions around as well, obviously, but Jen, look, she would like to know, why isn't the Earth bigger? Why does it end up being the size that it does?
Ooh, so the question of planet formation and how the solar system came into being, I think, is still an active topic of research. And especially because when we start, this is going to be me giving you a very long answer that basically boils down to we don't know. But when we look at exoplanets, so planets going around other stars, we don't tend to see ones that look like our solar system. So a lot of the systems, the planetary systems going around other stars that we found have planets that like are as big as Jupiter, but like closer into their star than Mercury is to our sun. So I think the discovery of exoplanets has pulled up all these questions about how do planets form, and why do you get your rocky planets and your gas planets, and why do they end up in the bits of the solar system that they end up in. And yeah, I think there's probably, and Katie might be able to expand on this a little bit more, I would imagine there's kind of a limit to how big like a rocky planet can form. That probably the gas giants, because of what they're made of, the differences, the gas giants can get bigger, but that's about as far as I can go with that answer. So that's a good question, because I like starting with a question that I can't fully answer.
Katie, would you like to add anything, or?
Yeah. So yeah, it's true that so it's true that we don't understand planet formation very well. So that's one aspect. There's also this really interesting thing I was just reading about a few weeks ago, because a new result came out about it, where there's as planets form, if the core of the planet is large enough, it tends to attract a large atmosphere of hydrogen and helium, and so that's why you get these gas giants in the outer solar system, because you have so much rocky stuff that's coming together. You also end up with a huge atmosphere, like it just has enough gravity to pull in a huge atmosphere. And there was a discovery a few weeks ago of a planet that was a rocky planet that didn't have a huge atmosphere, and it was orbiting very close to its star. And there was this idea that maybe what happened was that it had been a gas giant, so it had this huge atmosphere, and then something happened to it. It was like some other planet passed by it too close or something, and it tore the atmosphere off. And so it was something that was too big to be just a rocky planet without a big atmosphere envelope, but it was that, and it looked like it was this sort of stripped core of a giant planet. It was a very, very cool result that kind of gave some insight into this process, where the fact that those things aren't seen, it was sort of a Neptune-sized rocky planet. The fact that those things aren't seen is a clue to the formation of these things. So generally speaking, I mean, I'm not a planetary scientist, so this is all sort of secondhand knowledge for me. But it seems that once a planet gets too big, too massive, then it gains this huge atmosphere, and then there's crushing pressures, and it's very hard for the kind of life that we understand to form on it.
And that, I think, has also helped answer. Kevin had a question, which was, what is the smallest that a gas planet can be, and what's the largest that a rocky planet can be? So kind of, I think some of those elements have hopefully he's got some clues in there. This is for Helen. This is from Jahid, who said, this isn't an astrophysics question, but I'm sending it now while it's on my mind. Is the old phrase hot air rises literally true, or is it more the reverse, where cold air is pulled down by gravity?
It's more. He's right. It's more the reverse, that cold air is pulled down by gravity. So all of this, you need gravity for it to have any convection. Any buoyancy depends on having gravity, and hot things doesn't always happen, but almost always tend to expand, and so the same amount of matter just takes up more space. And what that means is that if you have another bit of gas next to it that's cooler, the atoms are closer together. This one within a fixed volume just has more atoms, it's all closer together. So it's a battle for gravity is pulling on both, and the one with more mass basically wins. So really it's quite literally a race to the bottom. So we think of buoyancy in terms of things rising, but actually the things that are rising are being squeezed out of the way by the things that are better at being pulled downwards. So yeah, and this is why candles work, for example, that candles, your hot stuff gets out of the way, it heats up, it rises, and it goes up, and it means it's gone, and it draws in cooler air, so then you've got more oxygen that can combine with your fuel to form more combustion. So actually these convection currents are really gravity is really important, but it is always the sinking that matters. And of course it does really interesting things to flames on other planets. So I played badminton, I had badminton coaching for the first time last week. Badminton coach hasn't seen me for 5 months, came in, I've got a question for you, and it was about a fire extinguisher in a film, in a space thing, And he was like, what was in this fire extinguisher that it poisoned everyone? And basically, fire doesn't work like that in space. So my badminton coaching session started with a 5-minute lesson on fire in space. And then we got onto shuttles. But the point is that buoyancy is really important for all kinds of things we take for granted. But it absolutely is a race to the bottom, not it's being squeezed out of the way.
So would a candle on the space station burn out because it wouldn't have that?
What you get is these spherical flames because unless you push it or blow at it in some way, it just runs out of oxygen in the middle because there's no reason for that gas to be refreshed. So I'm sure they do have some kind of fire extinguisher on the space station, but it's pretty much it's likely to be blankets, I reckon. I probably should have looked it up after that conversation. But yeah, things do the worst thing you could do on the space station if there was a fire is try and blow it out, because you would just be bringing more oxygen in to keep the combustion going.
Well, as we know, Apollo 13 started with a birthday cake accident, so which has often been covered up, of course. This question for you, Jen. This is from D1456. So I presume this is one of the AI programs which is trying to pass its Turing test. And the wonder was, she or he wondered, how far away are we from having a real problem, if we're not at that point already, with the growing number of CubeSats from SpaceX, Amazon, etc. I've heard astronomers on social media saying it's already an issue for observing.
Yeah, I guess what you mean by it kind of being a problem, being an issue. Certainly for observing from the Earth, these satellites already have a huge potential to cause problems for amateur astronomers and for professional observations. So I saw this being highlighted really well with the recent comet that was visible, Comet Neowise, and someone posted a picture that they tried to take, and it was just completely streaked by these little white lines that were some of these satellites, the Elon Musk ones, the Starlinks that had happened to go across. I think that there's conversations that are going on between professional astronomers and companies like SpaceX to talk about how to mitigate them. My husband and I were actually talking about them the other night because we saw a bunch of them just after one of the launches. One of my friends texted me and said, "Jen, why is the sky moving?" And I went, "Wait, what? Have you been drinking too much?" And then I went outside and because they recently launched, they were just so bright, just these like little trains of dots going across the sky. And my husband was saying, well, we haven't seen any for a while. And I think that as they go further up in their orbits, they become less bright because the only reason we see satellites is because they're reflecting the sun's light. And SpaceX had been talking about painting them so that they don't reflect as much. I think that will have be a big help for the amateur astronomy side of things, people who are wanting to do astrophotography as a hobby. But when you're talking about the most sensitive optical telescopes that we have, even painting them will probably pick up some things. And then you've got to remember as well that these satellites, they're not just visible in the optical, they're also going to cause a lot of interference in the radio. So my background is in radio astronomy, and these satellites, obviously, if they're the reason that SpaceX are putting them up there, one of the reasons is to do things like beaming internet down into remote parts of the world, which is a very worthwhile cause. And I think we shouldn't lose sight of the fact that that's the kind of reasons why a lot of the times these satellites are being launched. But if it's doing that, that's going to cause huge amounts of radio interference for our radio observations. So I've not been involved in those conversations directly. I know it's from talking to other people, it's certainly an issue at the moment. It could, maybe we're just about in the point where these things could be mitigated. But if all the satellites get launched, then that's going to cause a huge problem. The other side of it is obviously just having so much stuff in space orbiting around the Earth that you get to the point of thinking about scenarios like at the start of Gravity, where satellites are crashing into other satellites and having this cascade effect of space junk going around the Earth, which is another thing that I'm not quite sure. I would hope and I would assume that every satellite that gets sent up at the moment, I believe you have to have a plan for when that satellite's time comes to an end. So I think at the moment you either send it up to what's called a graveyard orbit, so somewhere further out, or you have a plan to have enough fuel or whatever to safely deorbit it so it comes back to Earth, it burns up in the atmosphere. But yeah, it worries me slightly. Maybe I've watched disaster movies too many times.
So I interviewed an expert on that recently, and they are terrified because the problem is it only takes one mistake.
Yeah.
And the other thing actually is the bandwidth, because the bands they use to communicate are getting close to the bands that the Earth observation weather satellites use. They're nudging in. And so actually, if they start to take over those wavelengths and cause interference, it means it reduces our accuracy of being able to detect types of rain and clouds and the amount of water in the atmosphere. And that means our accuracy in predicting weather might actually go backwards.
And I think this is
observations that are as good.
This is one of the things where I'm very cautious about private companies coming, kind of accelerating our kind of spacefaring ways and having more companies like SpaceX who are able to launch. And I don't know whether we've yet had those conversations about like responsibility and that kind of thing. It's one thing when it's a government agency like the European Space Agency or NASA or JAXA or whoever it is. There's accountability there. There's things that have to be thought about. But for private companies, it's kind of a bit more open. And I think with these SpaceLink satellites, no one kind of realized until they were up there what the effects were going to be. So yeah, it's a bit concerning for me, but we'll see what happens.
And there does seem to be, we can't help but notice a certain amount of ego within the games that are being played at times. I should just quickly say, by the way, an apology that about 15 minutes ago, apparently we had a drop out of sound for a couple of minutes on YouTube. Hopefully everything is working fine now, but apologies to anyone watching who found that it wasn't your laptop. There was a technical problem. Also a reminder, by the way, that we could probably fix that problem a lot quicker if you subscribe to us via Patreon, or just put something in the tip jar. So there we go. These then we'll find a whole new system, and we'll have a utopian way of doing our Sunday Science Q&A, or whatever the proximity to utopia is we can get to. This is about the Big Bang, and this is an interesting question. Well, I mean, they're all interesting, but this is because it involves the idea of a centre. And so I'm going to ask you this, Katie. This is from Printers United. Said, if the Big Bang occurred at the centre of the universe and the universe is constantly expanding in every direction, does that also mean the centre of the universe is always the location of the observer, therefore there is no true centre? So there's quite a few things I think left, but I will hand that over to you.
Okay. So that question went in a different direction than I thought it would at the beginning. So a lot of people ask about the center of the universe in terms of where did the expansion start, or where does it all come from? And the answer is that the expansion was everywhere. The Big Bang is a phenomenon that happened everywhere in the universe, where what we think of as the Big Bang as physicists is just the idea that in the early times, the universe was hot and dense and sort of in some sense smaller than today. And so every part of the universe was hotter and denser than it is now. And you can have that happen everywhere. And whether or not there was ever a singularity, so a sort of single point, everything condensed into a single point, we don't know. And then we have reasons to be skeptical of the idea that there was ever a singularity. But what we do know is that every part of space that we know about now was at some point hotter and denser than it is today. And so you can think of the Big Bang as it really happened everywhere. And the universe may be infinite in size, may always have been infinite in size and just getting bigger. There is no center from which everything happened. And so the way it looks to an observer is if you are in a point in the universe, any point in the universe, and the universe is expanding, what it'll look like is everything is moving away from you. And that'll happen where you are. It'll happen to, somebody 3 galaxies over. They'll also see that everything is expanding away from them. So we are all at the centers of our own observable universes, meaning that every point you are at, you see the universe expanding around you, you see things moving away from you, and you have a limit out to which you can observe, which is the edge of the observable universe, of your observable universe. So there's a sphere around you of about 46 billion light years in radius, out to which you cannot see past that, because that limit is the limit where if light left a certain point at the moment of the Big Bang, it would only just be reaching you now. And so the distance where that is true is about 46 billion light years right now. So every person, every observer anywhere in the universe is the center of their own observable universe, and that observable universe is the same size for everybody at the moment. And it would have been a different size at different points in the cosmic history. But yeah, so you can think of yourself as the center of the universe, or you can think of there is no center of the universe, whichever way you prefer. But there is no center we can go looking for and define.
I like your joke in the book where you say, if you are egotistical enough to think you're the center of the universe, remember that everything's rushing away from you all at the same time as well.
Yeah.
This is, but that's it. I mean, this is, sorry, I'm really, I kind of obsess about things that we picture or try to picture, and how we then, especially for lay people like me who are not able to understand the equations. Because I was thinking, I was watching something about the Big Bang the other day, and it will always be illustrated in documentaries, or certainly anecdotal, obviously, what I'm saying now from the ones I've seen, as a kind of explosion, as almost, and it expands out, and there is light, which is what the first 300,000 years, is it roughly? There's no light.
Yeah. Well, the first 380,000 years, the whole universe is a plasma, and then after that it gets dark, and then you get galaxies after about 500 million years or something.
So do you have what would you say if you were trying to give people an illustration of that, back to the point where of understanding, what do you think is the most useful?
So the way I have illustrated this sometimes, and the way I do it is just a blank white screen that then sort of fades to a red screen to a black screen. So that's what it would look like you were there. It would be very, very bright, and then the brightness would fade and redden, and then it would be dark. So in the beginning of what we know of, the universe is full of plasma. It's like being inside a fire. Only it's sort of an extra nuclear kind of fire, and then and you can't see around you. All you have is this brightness around you. You can't see through it, and then over time it dims, and then you can see through it, but there's nothing to see because the stars haven't formed yet. So it's not something that looks particularly exciting at the beginning, because there's just not that much going on, that other than, this extraordinarily hot, dense state is cooling.
Brilliant. Thank you.
I want to know whether any little raised, like a haptic screen that goes up and down. Can someone arrange that, Jen? Can you get, let's say that you feel the brightness and there's a little hill and then it goes away and then you feel the galaxies popping up. Someone should do that, I feel.
That'd be cool. Yeah. I have seen a 3D printed globe of the cosmic microwave background, which is the cosmic microwave background is the afterglow of the Big Bang, where we have this glow around us in the cosmos at the edge of our observable universe. Because that's where you're seeing back to the Big Bang, you see that primordial fire at the edge of the universe, and it's got little ripples in it. Basically, there's little spots in it from places where the fire was a little bit hotter, a little bit cooler. I keep saying fire, and people might take issue with that if they're being very technical, but don't. Anyway, there are places where it's a little bit hotter, a little bit cooler, and so it's a sort of bumpy picture. And I've seen that made on a globe, which is very cool, and you can kind of feel the variations in the cosmic microwave background. So that's the closest I've seen.
Yeah, I think it's
Jen, go on. Sorry.
Yeah, no, I was just going to say, I think it's an interesting thing to think about, of how, as Helen said, like, how do you represent it? Because those first like years of the universe, those first 380,000 years, the universe, because we can't see it, as you say, what are the other ways maybe that we could represent them? Is there ways with vibrations or 3D printing or whatever, having a tactile way? I've heard audio versions of what the Big Bang would sound like, and all of that kind of stuff. But yeah,
because it would sound like because at that time space was loud, because there were these fluctuations. There were pressure waves going through this hot plasma, which I think is very cool. And so that would have been sound. We call it acoustic peak or like acoustic variation, acoustic waves, and it is sound. It's that the universe was so dense it was loud.
Helen, this one is from the Reverend Richard Coles. If you're watching, Richard, hello.
I'm impressed he tunes in. That's
well, he might not. He
dedicated.
might tweet, but it doesn't necessarily mean he watches. He might have had a question some days ago. This is, as usual, I always throw all the ecumenical matters towards you, Helen. And don't worry, it's solar radiation. As solar radiation increases, at what point does life on Earth, as in our life, human life, become no longer viable?
So is he referring to the sun kind of burning out? I
think so. I think that's so. I think that's what, as in that kind of, yeah.
The reason it's an interesting question is because there's a difference between what you might need to get life started and what you need for it to continue. And actually, so I say quite often that the Earth is just like a dam in a flow of in a river of energy, and the energy comes from the sun. It kind of gets stuck in Earth for a bit, and eventually it flows out away into space, kind of through the cracks, through long wave radiation. And if you look at that flow through and you look at the amount of it that life uses, like, plants that gets taken up in plants, it's a really small fraction. Most of it goes into shifting around water, frankly. That's what it's doing. And so the amount of energy you actually need for life to keep going is probably quite small. However, if you lose all the other energy, the energy that is shunting the water and creating the weather and causing, sort of irrigating things and causing rain, you lose all that help from the Earth in maintaining your environment. So I reckon if you were going to, go to one of those sci-fi scenarios where you just existed in a little bubble in space and you had a perfectly efficient system and you just collected the sun's energy and used that to keep humans alive, tiny bit of energy, wouldn't take very much at all. So you keep going for a very long time. If you're talking about the amount of energy you need to run a planetary system and have a biosphere that's planet-sized, that produces the sorts of environment it needs for humans to live on, it's not quite as long, but it's still quite a long time. So we don't use, there's some caveats around the word use, but we don't use very much of it. So as long as we can adapt to Earth being a bit different, we could survive with a lot less. But I don't think we should try for that approach. Not for a long time.
I saw this question come in on Twitter, so I have a couple of things to add to this. I like thinking about the end of the world. I don't go quite as far as Katie as the end of the universe, but I do like thinking about that scenario about the Earth coming to its end, because the sun has only 4.5 billion years left only. Into astronomers, not so much time, 4.5 billion years. And so a lot of people think, well, that's the point at which, the sun will shed off its outer layers. The core will collapse down. There won't be enough heat for life on Earth anymore. But actually, because in that process of the sun coming to the end of its life, it's slowly going to expand and get bigger and bigger, and it'll get so big that Mercury will be inside it, and then Venus will be inside it, and then maybe the Earth will be inside it. We don't quite know, because it's going to stretch out to be about as far out as where our orbit is. But in this process, the Earth will actually shift slightly further away from the sun because it's going to lose some mass. And so there was a study that was done that said that in about, I think, 1.75 billion years, around that point is when all the water on the Earth will have completely evaporated from the sun, kind of getting closer to us and heating up the Earth. So that, to me, is the end point. If we haven't got off this planet, once there's no water, there's no hope. The other thing that I notice is that apparently, and I've not looked into this, I'm not a solar physicist, but when you look at the activity of the sun, and this might be what the question was referring to, the sun goes on this 11-year cycle of activity and then quiet times. But when you look at the amount of basically, the radiation coming from the sun in the quiet times, that's been slowly creeping up. And so there's an instrument on the International Space Station at the moment that's wanting to measure that, and see what the long-term, people start wanting to be able to blame climate change on this. But I don't think there's enough evidence either way to say whether the changes in the level of radiation coming from the sun is enough to push any of this climate change.
I think it's very, can I just jump in? It's very clear that climate change has nothing to do with any of that.
I was going to say, I am firmly,
there is very strong evidence that it might make a minor effect but it is not causing climate change.
Yeah, I'm firmly in the camp that humans are absolutely accelerating it, and everything that's happening now is our fault. But I think there is that question of what's the like longer term changes in the longer term for humans, not longer term for astronomers, changes in the radiation coming from the sun, and what kind of effects that would have on the Earth. As I said, there's no evidence yet. I think some solar physicists at NASA have been studying it for about 40 years, from one of the reports I found, and there's no evidence that it's having any effect.
Jem, while we're talking about the end of the world, this is from Renato. Would like to know: is it theoretically possible for a black hole to exist on a planet like Earth or Mars if the planet were big enough? Now, this is because, of course, people will remember when the LHC was first operating. There were certain rumours going around, certain kind of conspiracy theories about these small black holes that would come into existence and lead to the end of the planet.
So I think for me, black holes, there's a bit of a difference between the types of black holes that we talk about. So the black holes that I like, that I used to study, are the supermassive black holes in the centers of galaxies. Those are maybe like a billion times the mass of the sun. And then you have your stellar black holes, which I think are probably the classic black holes that most people think about, which are the ones that come about at the end of a massive star's life. It goes supernova, or you get a hypernova, and then the core collapses down to black hole. And then you have the kind of teeny tiny black holes that it was the kind of thing that they were talking about could have formed with the LHC turning on. I think it's actually a really sad story, the way that was communicated. I think at least one person took their own life because they were worried about the effect of that. So I think it's not something to kind of dismiss, and I think it's a failing of us as scientists to have not maybe communicated that out better, because Katie will probably be able to expand on this much more. But those kind of black holes that you're talking about, they kind of, in that scenario, would have been created and then like evaporated pretty much straight away. They can't sustain their being, if you like, on Earth.
I think it's also not always just down to science communicating. I think it's also a few more pages of the newspaper and mass news media would come in handy. I'm going to ask you a follow-up black hole question, Katie. So if you want to add anything as well, this is from Elizabeth, who wants to know: I can't get my head around something I can't get my head around when it comes to black holes. Is doesn't a black hole always get bigger because it's eating the nearby space and matter? But then I thought Hawking radiation meant that it's also losing energy and also presumably size. So is this sort of yin and yang situation that keeps the black hole alive, so to speak?
So black holes, the black holes that we know about, that we know exist in the cosmos, none of them are evaporating right now. So black hole evaporation, Hawking evaporation, is something that happens if you have an isolated black hole that's just sitting there and there's nothing falling into it. There will be this kind of quantum process near the black hole event horizon, the sort of edge of the black hole, where it will lose mass very slowly over time, and it'll speed up in the way it's losing mass as it gets smaller and smaller. For the massive black holes, the ones that we know about out there in the universe, they are pulling in matter. We, generally speaking, only know about them because they are pulling in matter, and so those ones are growing. So the evaporation process is so slow for a massive black hole, anything bigger than anything that could be formed by a star or something like that. That process would be so slow that anything that's falling in would massively overtake that. So those are gaining mass. So the way that the black hole mass changes, either stuff falls in, or if you leave it alone long enough, or if it's small enough that it will evaporate. But all the black holes we know about are the ones that are too massive to be evaporating at any reasonable rate at the moment. So in principle, if you could make a very small black hole, then it would evaporate quickly and it would be bright because it would be putting out all this radiation as it's evaporating. But we don't know how to make small black holes. So there's this idea that the Large Hadron Collider could have done it, was something that was sort of hoped for as a way of, we'd learn something about some interesting theories of gravity if it had happened, if you had made these little black holes. But so the 2 points about the little black holes, well, 3 points about the little black holes, why we shouldn't worry about them, even though we do kind of hope that they do form at the Large Hadron Collider. One is that yes, they would evaporate very quickly as far as we understand from the theory. Also, because the collision would never be so perfect that they would stop in midair, like they would be moving very quickly away from the Earth one way or another. Even if they went through, it would be so low mass that it would just go right through and leave very quickly. And also, anything that our particle colliders can do can be done, like has been done for billions and billions of years by cosmic rays out there in the universe. So we can't make a particle collider more powerful than the cosmic ray collisions that we know are happening out there in space. And so you have very similar particle collisions kind of happening out there in space, but at much higher speeds, much higher energies. And if those have not destroyed the universe or, the moon or whatever, or, created horrible things in our upper atmosphere, like if that has not happened for the last billions and billions and billions of years, then us, slamming stuff together at our machines is nowhere near going to do it. So
how would you find out? I think they sound quite cute, these little black holes. But say you made a little cute little black hole LHC, how do you know it's there? Because it's too small, presumably, to have any gravitational effect. By definition, it's either black or, as you said, it's radiating.
Yeah,
I suppose that'd be quite noticeable. How do you find a tiny black hole? Black hole.
So there are two things you can look for. You can look for the Hawking radiation. So because it's so small, it would be radiating quite a lot very quickly and more, much more in one direction than another. So you'd be able to, because it'd be moving, so you'd be able to see sort of a burst of radiation. If it were not radiating, what you would see is missing energy. So you would see that the collision happened and you can count up all the debris and there's something missing from that debris that you don't get as much out as you put in, and that would tell you that you made something interesting. So missing energy signatures are also used to look for dark matter, because if we can create a dark matter particle, then you would also see a missing energy signature.
Right, we're pretty much at the end of the show. We've had loads of great questions. I've got the mass of the universe and the shape of the universe, and you can find stuff on this from our guests, and we'll skip this. Also, there's some way. Where's your story about being heckled by Stephen Hawking, by the way, Katie?
That's in a number of places. There's if you go to my website, astrokatie.com, there are a couple of links right on the sort of homepage, and one of them is a podcast where I talked about this for the ABC, I think, a while ago. So that might be the place, the easiest place to find it.
Yeah, there's a nice story. Leonard Molodnov has got a new book about his friendship with Stephen Hawking, and the first thing Stephen Hawking ever said to him was banana. And there's a lovely story about that first particular meeting. Jen, where's the best place for them to find out what you're up to and the work that you're doing?
So I'm on Twitter, Jen_Gupta. That's probably the best place, although I think mostly I'm tweeting pictures of hedgehogs from my garden. I work for the Institute of Cosmology and Gravitation at the University of Portsmouth, so you can Google that and find out some of the stuff I'm doing there as well.
There's a lovely little book called The Hedgehog Book, which is by Hugh Warwick. I don't know if you've ever met Hugh or whether he was ever at one of the Christmas shows, but Hugh's got a new book. He's a great hedgehog expert, and he's a lot of fun. So the final question: we don't have time for whether dinosaurs, if they'd had telescopes, whether they could have managed to work out some kind of technology to avoid the cataclysmic collision that seemed to be one of the main reasons that led to the end of them. So instead, let us merely talk about the end of the universe. From each one of you, do you have a favourite scenario when it comes to the end of the universe? You may base this on scientific supposition, or it may well be something fantastical from your imagination. Let's start with you, Katie.
I'm going to pick the obvious one. I think the restaurant at the end of the universe is a great thing. Let's all have a very big viewing window. Let's all sit down to a nice dinner and watch it happen. I'm all on board with that. I really like transparent things so you can see how they work. So I really like the idea of the end of the universe being basically a transparent thing so you can see how it works just before you all snuff it.
So the booking for Milliways for you. Katie? we all hope that eventually, you know, we go to the pub and we die in our sleep at the end of that. It's that kind of version of the end, isn't it?
Yes.
Jen, what about for you?
I don't know. I'm a bit more cynical. As I said, I spend far too much about how the universe in terms of humanity is going to end and how we're going to screw it all up and kill our planet.
It's an interesting thing, isn't it, where the existential anxiety is in terms of, because Paul Dirac talked about the fact that, you know, he was totally happy with or as far as you can be content with the end of his existence. But when he found out, you know, when he started to think about the end of the universe, that troubled him far more. The fact that all of that physics that he had done, not for his own ego, but merely for the continuing building of knowledge, the fact that all of that will be wiped out was far more troubling to him than the termination of his consciousness.
Yeah,
I find it interesting for each one, you know, in terms of that existential anxiety. How does
it? The Library at Alexandria, isn't it? The fear of every academic is that knowledge would be wasted or just lost. Even if we don't think of ourselves as hoarders, academics are fundamentally all hoarders of knowledge, and the idea. It's like having to. I mean, Robin, I know you do this a lot, but it's like having to get rid of books. You know, you can't. It's very hard to get rid of a book, and academics are like, no, but it's matters. People have thought things. We want to know what they thought. So we're all just hoarders. Maybe it's just going to clear up our hoarding habit.
Well,
yeah, it's a very hard. It's a very hard thing to come to terms with, the idea that knowledge will be forgotten. That is definitely one of the most terrifying things for me about the end of the universe.
Well, we end the end of the universe, but there is no but. The universe will return in Moonraker. No, that's it. But then again, also we still don't know. So it's thank you all for joining us. And as I said, Katie has of everyone on has the book that's come out most recently. So we'll plug again the end of everything, and hopefully we may well, as I said, one of the things that we are planning on doing, the 9 lessons and carols for curious people that we do every year. If we are unable to do that actually physically with an audience in front of us, our plan is to do a big event at some point later in the year. We'll be back next Sunday with another Sunday Science Q&A, and if you check the Cosmic Shambles site, etc., and Twitter feed, and my own Twitter feed, which I'm not on Twitter, by the way, that's all done by Trent, so that's why I have no conversation with people there, but that's where we'll also keep you up to date with who's going to be on next week and the questions you can ask. Don't forget, Jay Wilgoose is on the latest show and tell from Public Service Broadcasting, which is a very interesting conversation, and he ran out of things to show, so eventually we just looked at his guitar. It was lovely. It was a great guitar, and obviously all the book shambles are still up there, and there's more book shambles coming, and we've got Tim Harford coming up and various others. Thanks very much. Please do support us via Patreon if you can, and enjoy the week that you have ahead of you.